Okay, students, this is our lecture on calcium and magnesium. This is the handout that I did not get to you, so you won't have this in your pack because I couldn't get it printed out the day I was trying to do it. Let me move this over just a little bit. Okay. So as we look at this is written by Dr. George Raym at University of Minnesota, and we're still going to be talking about calcium and magnesium, and sulfur is usually grouped in with those secondary macronutrients because they're secondary nutrients. They aren't primary like N, P, and K. But a lot of times, because of the charge, the Ca2 plus and the Mg2 plus are grouped with potassium, which is a 1 plus, and they're referred to as our basic cations in the soil solution. So usually sulfur and potassium are discussed in separate lessons when we go on this and strictly stick with calcium and magnesium. So we're going to look, it says here, it's looking at the importance of calcium and magnesium in Minnesota soils, but we could pretty much put that across the scale when we look at calcium and magnesium in soils. And again, they both exist as cations, and so that's a positive charge. Both of them have a +2 charge. And your clay-sized particles that we have are all negatively charged because they're organic matter. So basically, it says similar electrical charges repel each other while opposite charges are attracted to each other. So our calcium and magnesium are attracted to and in close association with those negative charges that are here on my clay-size organic matter particles. Okay, so if we look right here, it says this figure intends to show there is no actual locking of cations to the soil particles, but there's an association between a cation with 2 positive charges and 2 negative charges on the soil particle. So the calcium hooks up to 2 negative particles on the soil. And here we can see them occupying the surface on clay and humic material. So it's just giving you a certain percentage. So it tells you that on the clay we have about 60% calcium. Here we have 20% magnesium, 10% K, and 5% ammonium, and 5% hydrogen. And that's just what it says here. So what are the importance in plant growth? So let's just look at calcium first off. Calcium is a part of every plant cell, and the biggest portion of what, I didn't mean to do that, sorry guys, I'm sending this all over the place. Okay, Gwen stopped. Just going to leave it. Okay, so a lot of the calcium in your plants is in the cell walls, and the compound is called calcium pectate in the cell wall. So this pectin or pectate keeps the cell walls from collapsing because the plants wouldn't remain upright without it. And notice calcium is not mobile in plants. It doesn't easily move from the old to young leaves. So deficiency symptoms for calcium are pretty rare in agriculture, and deficiency symptom of this nutrient is not a concern in Minnesota. We have adequate calcium here. It's not a concern for us in eastern Washington. It can be in western Washington, although I can tell you I don't think I've ever seen a calcium deficiency on a plant. Mainly because what happens is that the plant just doesn't grow well, it doesn't use nitrogen efficiently, it doesn't really show on the plant. The processes just don't move or happen as quickly as they should. So our bulletin here says calcium also has a positive effect on soil properties. So this can help with the flocculation of the soil. So it says it improves soil structure and increases water penetration and makes it a more favorable environment for growing plants. So for uptake of nutrients by plant roots and soil microorganism populations. Calcium is abundant in Washington, pretty much central and eastern, and fairly deficient on the west side. So your concentration in a form usable by plants could be as low as 300 to 500 parts per million in our acid soils, and where we have highly calcareous soils with a lot of calcium, it can be up to 7,000 parts per million. In this part of the country as well, calcium is usually not needed in a fertilizer program. Even at our low levels, there's adequate calcium for crop growth. But when we do have concentrations of calcium that are high, your free Ca+2 reacts with phosphate, and it will form an insoluble calcium phosphate in the soil solution around the soil. Okay, before I go on to, where's my camera here? I'm going to finish up with calcium. We've got two little things to go over here. If I can get this together in a minute. Everything's all around each other here. So what I want to look at here is, this is our summary article. If we look on the, I'll just look on the front page. This is out of the book, so it's got, this is what's on the front is the root, so that's page 258. So we're going to go over to page 259 with the distribution of, oops, nope, wrong page. We're going to go to we are going to 259, but we're just going to go to calcium. Okay, so if we look at calcium here, and I'll just make it closer so I can read down what's going on. Again, this is just what we said. Calcium has several structural roles. Deficiency can be a problem if the plant can't transport calcium to rapidly growing tissues fast enough, and that will result in tissues collapsing and becoming soft and spotted, as seen in tip burn of lettuce. So it does happen. The other thing that happens is what they were talking about in that one video clip today, that when you have insufficient transport of calcium into rapidly growing tomato fruit, you can get a brown patch on the bottom called blossom end rot, and it makes the tomato unmarketable. I've had that, but it's mostly caused, in my case, by irrigation later in the evening, so that it's improper timing of irrigation, so I get blossom end rot. Okay, so calcium deficiency, as we look at it here, has also been implicated in improper development of poinsettia bracts. So if we go into the timing of when the poinsettias are supposed to be changing colors, it's very important to have calcium. So what they do in greenhouse situations is they apply calcium oxide or calcium nitrate to prevent the problem. And calcium nitrate's a great fertilizer. You can just get some burn with it, so you have to be careful. Again, applications are especially effective during times of rapid growth or cell expansion, because these are available immediately, and especially when they follow periods of slow growth, such as cool or cloudy conditions. Okay, so for deficiency symptoms, along with what we've described above as far as the blossom end rot and the plant's collapsing, the top of the plant can develop a twisted, distorted type of growth. And I have never seen that in plants with calcium. Okay, before we go on to magnesium, let's just look at calcium uptake again. This is the handout that you got. Okay, it's got the SMART on the top. It says calcium in plants. And we're just going to look at mobility and uptake. So the one thing we want to notice here is calcium uptake by the plant is passive, so we don't have to have ATP to bring it up or to get it into the plant. Your calcium mobility in the plant takes place mainly in the xylem with the water, and therefore calcium uptake is directly related to the plant transpiration rate. So if the plant is photosynthesizing and transpiring, calcium will be taken up by the plant. Where we have conditions of high humidity, cold, and low transpiration rates, because of the slowing of that transpiration rate, you can have a calcium deficiency because it's just not taking it up. The other thing that can cause it would be a salinity buildup, because pretty much the sodium, Na+2, calcium, Ca+2, the salinity buildup can cause or decrease the water uptake by the plant too, because of the nutrient loading. Okay, and again, because we said that calcium mobility in plants is limited, the calcium deficiency is going to appear in the younger leaves as dieback or burns, and in our fruits, which is, we talked about blossom end rot. I'm not sure what bitter pit is, but I probably should know. But anyway, it's because they have a very low transpiration rate. So it's necessary to have a constant supply of calcium for continued growth. It is an essential plant nutrient, okay, but it's a secondary one. And what does it do? We've already talked about these items, but let's go back through them. It participates in metabolic processes of other nutrient uptake. It promotes plant cell elongation. A very important one is strengthening your cell wall structure, because without it, you won't have stability in the plant. It also is involved in some of your enzymatic and hormonal properties or processes that take place. It's part of protecting the plant against heat stress, so calcium improves your stomatal function in the plant. Okay, it helps in protecting the plant against disease, simply because there's a lot of fungi and bacteria that will secrete enzymes that can impair the cell wall. So the stronger the cell walls induced by calcium, the more it can avoid invasion by other diseases. It affects fruit quality, and it actually has a role in the regulation of stomata along with the potassium in the stomata. So let's look at what are some of the factors that affect whether calcium is available to plants. The main thing is that calcium can form insoluble compounds, so calcium phosphate. So basically that's not available to the plant, so it can't take it up. And because calcium is positively charged, it can be adsorbed in the soil to the surface of the clay, and organic particles which are negatively charged, so it can be relatively unavailable there too. So positively charged ions that are adsorbed to the soil particles are termed exchangeable ions because they can be exchanged by other ions present in the soil solution. So your soil test or soil analysis determines the level of the exchangeable calcium ions and not the total calcium in the soil, because your exchangeable calcium is the form which is available to the plant. So that's why they look at the different methods for extraction with different soil types. Okay. So let's look at this last couple sentences here. So there are several factors in the soil analysis that can help in quantifying or assessing the availability of calcium to plants. So when we look at soil pH, usually our soils that have a higher pH contain more available calcium. Okay, that's one fact. The cation exchange capacity is a soil characteristic that describes the total amount of positively charged exchangeable ions that the soil can hold. So if I have a higher cation exchange capacity, it would indicate a high capacity of the soil to adsorb and hold calcium, and therefore higher calcium availability. If it can hold it, it can exchange it. And then we also have to look at the presence of competing ions within the soil solution. So calcium competes with other positively charged ions, and those would include sodium, potassium, and magnesium. Okay, notice that magnesium is a direct 1-to-1 ratio with calcium, and sodium and potassium are a 1+, so there would take 2 of them to replace the 1 calcium. So if we apply too much of any of these positively charged ions, we can decrease plant calcium uptake by the plant. So sodium ions can replace the adsorbed calcium, damage soil structure, and decreases calcium availability, which is what happens in a saline soil. Okay, that's exactly what it does. Okay, we'll just look at the other last couple reactions of calcium in the soil. We can get a calcium phosphorus or calcium phosphite precipitation, so that means that happens when we have free calcium accumulate in the soil solution, and that's usually when soil pH is high, and the calcium will tend to form insoluble compounds with phosphorus. So not only is the calcium unavailable, but consequently phosphorus availability is also significantly decreased when this happens. And then the other thing that happens is that calcium helps us stabilize your soil structure, so that a calcium that is adsorbed to a soil particle helps stabilize it. Adsorbed sodium could cause the soil to crack when dry and swell up when wet. So calcium actually replaces the adsorbed sodium and prevents damages to soil structure. And usually the most common way to get a calcium deficiency is by having low calcium availability or water stress, which results in low transpiration rates, so it can't take up the calcium. So your symptoms of calcium deficiency would include curling of young leaves or shoots, scorching or spotting on young leaves, poor growth, leaf tip burns, stunted roots, damage to the fruit. So it looks like drought damage, which essentially it is, because it's also not taking up the water, but that's not the main influence. The decrease in transpiration rate can actually cause the calcium deficiency. Okay, so that's going to do it for calcium. So let us go ahead, and since I got the camera on already, let's go ahead and look at magnesium on this handout that we had from the textbook itself. We're back on page 259. So if we haven't really talked about the role of magnesium in plants. We actually did back in photosynthesis, because magnesium 2+ is an essential component of chlorophyll, and that's an essential part of photosynthesis. So it says here the second critical role of magnesium is in, oh, where'd my page go? Oh, it got all out of order. Sorry. Energy transport. I knew it was here. I stapled them wrong. So watch your documents. These pages were out of order, so we're on page 260. So basically, it's a necessary component of ATP. And if we look at the formula here, it says the reactive form in ATP is the magnesium salt. So they usually have a substrate plus ATP gives you a product plus ADP plus PO43 minus. And the correct way to write that reaction is your substrate plus the magnesium activated ATP gives you a product, and the magnesium stays with the ADP, and the phosphate is by itself. So magnesium is the critical driver for energy transport in plants, or transfer in plants. If we have a magnesium deficiency, that's characterized by your intraveinal chlorosis of the leaves. So if you look at that, intraveinal chlorosis could be an iron deficiency too, as we'll see. It has it in figure 13-14, but in our document it's not shown. I mean, since it's not in color, it doesn't show up well at all. Okay, if we have a magnesium deficiency, we're usually going to apply something like magnesium sulfate or Epsom salts as part of a fertilizer mix, or even as a foliar application. We can do it in a spray solution as well. Okay, so while we're on this, I think the minor elements that we're going to go through. Let me see what I did with these pages. I apologize for that because now I have to go. So I've totally lost page 261. I apologize, guys, and I don't have it with me. So I'll have to come back to that and talk about iron. So I think for right now, I'm going to skip over iron because I lost that page. Ugh. Okay, let me get out of this particular handout. And go back to our module here. Okay, so I'm going to go in here and see if I scanned this wrong too. So I apologize if you're missing that one page from the. Isn't always something that goes wrong. Oh, we're getting all kinds of stuff here. Let me look in my book summary to see if I have page 261 in here before I totally shut us down. Okay, 258, 59, 60. Ha! I have 61. So we're going to go on with some of this here. Well, we can do a little bit. I've actually got 3 or 4 things that we can do about iron, but let's just finish this summary of the textbook, and then I can put our other elements in the other lecture so I have it all grouped together. So with my minor elements, probably the one that can be most efficient in soil is iron, and that's because it's very pH dependent. So if we get the pH too low, it can be unavailable, but pretty much once we get above 7, you'll see that it's basically unavailable. It ties up very rapidly, but iron is important in energy transfer and photosynthesis. It's actually tied into the photosynthesis. So iron is one of the immobile elements. It shows intervenal chlorosis, just like what we saw with magnesium. But this is, let's just compare though. Magnesium is intervenal chlorosis of the lower leaves, and iron is intervenal chlorosis of the upper foliage. Okay, so that would be the difference. So we can correct for that iron deficiency by putting on an iron sulfate or a chelated iron, which keeps it open, keeps the site open. It keeps it from tying up to the soil and becoming unavailable. So it actually fills that site so that it can't attach itself to the soil. When we do put on an iron sulfate, it has to go directly to the affected foliage. And in a lot of cases, what we can do is adjust the soil pH, so bring it down by adding sulfur to actually make the iron more available. Oh, this thing is jumping all over. I apologize. Okay, so if we look at, let's just finish talking about nutrient deficiencies. So in each one of these elements, we looked at deficiency symptoms. But the problem is that if we rely on typical nutrient deficiencies, they can vary from plant to plant and be very similar to other diseases and other disorders. So basically, you can't just examine the plant and leaves and decide that it needs more nitrogen without doing more tests. And that's where we come in with a soil test, and what we're going to talk about when I get back on a week from today is just a leaf analysis or leaf tissue analysis. So we have to make sure that without doing those tests that we do those tests so we don't make the problem worse. So here's an example they give you. If a plant shows nitrogen deficiency symptoms, that might be the result of too little nitrogen, but it can also be the result of damaged roots that can't take up the nitrogen or something interfering with nitrogen metabolism. So we need to take a soil test to see if we had adequate levels. Sorry, I forgot to turn my phone off. So we have to see whether we have adequate levels, but the leaf analysis would show a deficiency, and adding more nitrogen to the soil is not going to correct the problem because it's not taking it up. In fact, if we added more nitrogen, we could create a toxicity effect where if the plant wasn't taking it up, and actually if it was sitting in the soil, it could be a potential pollution problem if we had over irrigation or got more moisture than we needed. So what you should look at is giving a small amount of the nutrient if you suspect a deficiency, but at the same time you're doing that just to keep the plant going, is to perform those tests so that we keep everything moving forward. So don't apply more of the nutrient until a deficiency in the soil is confirmed, and basically samples of the soil or medium in which the plant is growing and plant tissue are sent to the laboratory for analysis. And there are a lot of companies that do that, and they usually get it done pretty quickly. So the testing lab usually will supply analysis of all major and most minor elements, and will give you a warning if the concentration of one or more elements is outside your normal range, which is what you're trying to find out. It does cost something to have this done, but it's probably the most reliable way to figure out what's going on in your plant. Sorry this keeps moving here, that I have nothing I can do with it. There are a lot of other places where you can visit to look at symptoms. And in the back of the book, they list some other sites you can go to for web searches. And if you go to each one of the university extension sites, they usually have information about specific crops as far as what will be the most common problem you'll see with nutrients and diseases. Okay, so the last thing we want to talk about is remobilization of these nutrients. So basically, the reproduction in plants is such an important part in survival that they have mechanisms in the plants to preserve nutrients for future generations. So this means that seeds of the plants are a really rich source of nutrients. So that's what's happening as that plant is developing, is if we have adequate nutrients as it's developing, all the nutrients are going to go into the seed, which will be its next generation. Okay, it also means that the plant will allocate resources to the seeds from other tissues and organs, and that process is called remobilization. So the three biggies as far as nutrients, nitrogen, phosphorus, and potassium, are really important in seed development. And there's a lot of these nutrients that are taken up from the soil solution during the growth of these plants. All three of nitrogen, phosphorus, and potassium are relatively mobile, and large quantities are moved from vegetative tissues to your reproductive tissues during reproductive or seed development and the onset of senescence in annual and deciduous perennials. So basically, as it's getting on in the season and it is maturing, the nitrogen, phosphorus, and potassium will be moving to the seeds so that we have something for the next season the next go around reproductively for the plant. Oh, the moving around of NP and K is actually on the next page. Hang on a second. Okay, let's see if I can put that on here too. Oh, I don't have the camera on. Okay. Well, I'll finish with this and then we'll look at the picture. Okay, because this is probably better available right here than using the camera anyway. Okay, so, you know what, I'm going to move this over. Let me see what I can do. I don't know. I can move this over this way. Okay, so let me see if I can put this in. I've not done this before, so this is, thank you for letting me play around with this. Okay, so this is the distribution of nitrogen, phosphorus, and potassium in soybean plants. This is the figure that it's talking about. So this is percentage of total, and this is days after emergence. Okay, and if we look at the actual amounts of nutrients from vegetative to reproductive tissue, that's what's shown here. So here's 100% nitrogen, phosphorus, and potassium, and it shows what portion of the plant those are related to. So it's just the relative depletion of nutrients from your vegetative tissues during the reproductive development. And what you want to notice is that nitrogen, phosphorus, and potassium, that there's an accumulation of nitrogen, phosphorus, and potassium during the early reproductive. So we see this right here as it's going up. All of them are coming up and keeps going here till we get to 100%. So there's nitrogen, phosphorus, and potassium. So it's moving in the reproductive development. But at about 85 to 90% here, it stops. Okay, and it levels off. So after 80 to 5, so if we look here at 85, this is days after emergence. At 85 days after emergence, just about all the way, it stops rising. And so there's no more accumulation. And then after that, we see that the nutrient content of the leaves, stems, and petioles start to decline. Okay, because they're highest here, and then they all start going down. So what happens is then all of that is actually going into the seed itself, into the beans. Okay, if these are soybeans, it's all going into that. So all those nutrients in there are going down, but it's filling up in here in my seeds instead. So between 85 and 120 days after emergence, the massive expansion of the portion of nutrients occurs in the beans or the fruits. So some of the nutrients are lost in fallen leaf blades and petioles, but by the time of leaf drop, much of the nitrogen, phosphorus, and potassium has already been withdrawn and remobilized to the seeds. So up to 84 days after emergence, it's in all the plant, and then it starts remobilizing into the seed itself. Okay, I'm just trying to move this over so we can go on. Okay, so what happens is this process that we're looking at here with them all continuing up until about 85 days, and then the rest of the portions falling off and filling of the beans happens in almost all plants, or it does happen in all plants that undergo annual senescence of some type of vegetative tissue. But you will notice that for some of the plants, the destination for the nutrients is the roots and not up to the seeds or the beans. But anyway, by harvest time, the nitrogen, phosphorus, and potassium content of your corn stalks or grape leaves or apple leaves is very low, and too low for those organs to actually be very functional. So by the end of the season, they're pretty much just made up of carbon, hydrogen, and oxygen, and they provide organic material when returned to the soil, but they don't put much of a nutrient, nitrogen, phosphorus, or potassium back into the soil, simply because it's already gone off into the roots or up into the leaves, as we've seen here. Okay, and we've already looked at that picture. So we'll just finish up our review of our textbook here for the end of this chapter, and then we'll go on into looking at some of the other micronutrients such as boron and chloride and zinc in the soil. So if we had to summarize all this, our nutrients are going to move into the plant root as ions through a complex system that involves free movement, your apoplast, and selective transport, the symplast, and the plasma membrane is where most of the selective control goes with the proteins. Once inside the root, the ions are going to be transported relatively easily through the xylem to other parts of the plant. So it's going to move up with the water. So the absorption of minerals into the root depends on the growth of the root and its features. And you can think of the roots as exploring the soils, and our root hairs are going to be the main site of our nutrient absorption. In our healthy roots, they have a large amount of root area. And if we don't have a lot of roots, we may have some other mycorrhizae, either endo or ectomycorrhizae, that will help with uptake of the nutrients. Okay, and nitrogen, phosphorus, and potassium are macronutrients, but our essential elements also contain carbon, hydrogen, oxygen, nitrogen, and the first three come from air and water. The rest are all nutrients from the soil. You go on with potassium, calcium, magnesium, sulfur, iron, manganese, molybdenum, copper, boron, zinc, nickel, and chlorine. Okay, so the ones down here that we haven't covered yet are going to be required in very small amounts. So mobility is an important classification for our mineral nutrients. So mobile elements can be scavenged from our older tissue to support the growth of new vegetative and reproductive tissues. So this remobilization is a very important point to cover. Usually nitrogen is going to be the element that most often limits plant growth because it's used in the greatest quantities, and it's involved or contained in proteins, DNA, RNA, and a lot of metabolites. Remember, nitrogen is not available as N2. It's got to be taken up as nitrate or ammonium, and much of the nitrogen in the soil is actually in an organic form, which has to be converted to a usable form during decomposition. And this is where you get some plants that develop a relationship with rhizobia bacteria, and those nodules, such as we see in soybeans and what else am I thinking of? Any of the nitrogen manufacturing plants, they actually convert N2 into ammonia via nitrogen fixation. And we showed that within our world we can make fertilizer out of nitrogen too, but it takes a lot of pressure and a lot of energy and is very costly to make. And that's what happens in the Haber-Bosch process, where we actually make our own fertilizers. Okay, so we can apply fertilizers, ammonia, urea, ammonium, and nitrate, but ammonia and urea have to be converted into our ammonium for uptake. Nitrate is easily taken up, but it's also the form that's most easily leached into the groundwater. And we talked about deficiency symptoms as chlorotic lower foliage, and we can apply a lot of different types of nitrogen. And then phosphorus is our most second limiting element. Remember, it's involved in ATP, It's involved in the structure and function of DNA and RNA, and it becomes unavailable as we get our pH above 8. So your soil pH influences availability. So below 6 and above 8 the phosphorus is not as available. So it's better to adjust it. If we don't have adequate phosphorus, our mycorrhizae can play a role in helping plants obtain that phosphorus. Remember, they come into the plant, and hyphae from the fungi spread out and extract phosphorus from areas distant from the root. So they act like root hairs. And if you have a phosphorus deficiency, it's going to be, the plant will be a dark green, kind of reddish purple color in your lower leaves. And remember, it's supplied in an inorganic phosphate form. The other thing, potassium, we talked about today, is critical for stomate opening or stomata opening and enzyme activity. We usually will put potassium in a little bit less than nitrogen for a lot of plants because it's retained in the soil in a readily available form. And again, deficiency symptoms are chlorosis and necrosis of the margins of the leaves of dicots, and your monocots start with the tip and then marginal chlorosis of the leaves. They showed some of that, Dr. Camerato showed some of that in that potassium deficiency in drought videotape that I showed. Calcium, important in structural stability, usually not deficient. Deficiency can be indicated by a tissue collapse. We talked about blossom end rot. In tomatoes, tip burn, and lettuce, we can apply calcium hydroxide or calcium nitrate as a foliar spray to help prevent the problem. Magnesium is part of the chlorophyll molecule, so deficiency can cause an interveinal chlorosis of my lower leaves, and we could add Epsom salts, again, as a fertilizer or as a foliar spray. And then lastly, for the things that we covered here in the book, is iron is involved in photosynthesis and energy transfer reactions. And pretty much deficiency occurs not just because of a low amount in the soil, but because soil pH is inhibiting its uptake. So it could either be too low or too high of a pH, so it's gotten tied up somewhere so it's not available to the plant. So we could apply a foliar application of iron to correct the problem directly to the leaves. Again, for all suspected deficiencies, you need to confirm it before you add much back so that you're not creating a toxic situation for the plants, because other problems can actually look like a nutrient deficiency. So soil testing and tissue testing are necessary to tell us what's actually happening. And the last thing is just the remobilization. Whereas plants get older, they reallocate nutrients from one part of the plant, like the leaves, the stems, the petioles, to the reproductive part, which may be the seed, or storing them in the roots to use for the following season. So N, P, and K are the most readily mobile, and elements like iron are pretty much immobile. Okay, so that's where I'm going to cut off our first lecture. So this was the lecture for Wednesday. You should have worked on your lab yesterday, and hopefully, well, not hopefully, but I'll have the other lecture recorded, and we will go through some of the last part of the iron, and then go through boron, zinc, chloride, and then, oh, I didn't talk about sulfur. So sulfur comes before the rest of those. So we'll talk a little bit about phytosiderophores and what siderophores are, and then we'll wrap it all up with mineral nutrition affecting plant diseases and how we can actually prevent diseases by having appropriate nutrient status within the plant. So thanks. See you with the next lecture.